let's consider water at its boiling point at atmospheric pressure. If we look at table B5, we could look up the internal energy values of water in both the liquid and the vapor phase. Okay? So for water at 100 degrees C and 1 atm, if we look it up in the steam tables, we could see that its internal energy for the liquid phase was 419 kilojoules per kilogram, and for the vapor phase it's 2,507 kilojoules per kilogram. So the vapor phase has almost a 5 times larger internal energy than the liquid phase. And why is that? Why are the internal energies so different? Well, we have to once again think about what the definition of internal energy is, right? It's describing all the molecular, atomic, and subatomic phenomena that are happening in each of our chemical species, right? And so when we consider the difference between a vapor molecule and a liquid molecule, remember that vapor molecules can move around much more freely and move around freely, right? And they have much more energy than densely packed liquid molecules are much more energetic than densely, oh, I misspelled densely packed liquid molecules. Okay? And in general, when a chemical species changes from one phase to another, we typically see a large change in both the internal energy and the enthalpy. When a chemical species changes from one phase to another, there is a large change in internal energy and enthalpy. Okay? And so these types of large changes that we observe, these are called latent heats. And that's because they occur, the change in enthalpy occurs without any noticeable change in the temperature of the system. So they're called latent heats because occur without any noticeable change in temp. Okay? Alright, and so let's visualize, these sorts of changes in the internal energy and the enthalpy. Alright? And so what you're seeing here is a plot of the enthalpy on the y-axis and temperature on the x-axis. And as we start on the left-hand side, we're dealing with some sort of solid chemical species, right? And so as we increase temperature, we see that its enthalpy slightly increases, which is consistent with the idea that the enthalpy is just is related to the heat capacity of the material. So the heat capacity would be the slope here. Okay? But when we get to a specific temperature, we see that the enthalpy of the system jumps. There's a step change here, right? It's not a smooth function anymore, but we just see a sudden jump in the enthalpy. And then our enthalpy continues at a new higher value. The jump that occurs here is known as the enthalpy of fusion. So we're going from the solid to the liquid here, all right? And so This jump here corresponds to the latent heat that's associated between the solid to liquid transition. Similarly, as we go through the liquid phase and we heat it up, we see another jump, right? And then after this other jump, we go to the vapor or the gas phase. And so the latent heat that occurs here is known as the delta H of vaporization because it deals with a transition between the liquid and the vapor phase. Okay? And a similar plot can be developed for internal energy as well. And so we could see just from this plot that there's actually many different types of latent heats that we can encounter. Okay? So different types of latent heats. Right? And I just want to catalog a couple of them for you in this video. Right? So the first one that we're going to deal with, since we're going to deal with a lot of liquids going to vapors and vice versa, is that heat of vaporization. Okay, so you'll see this abbreviated as H sub V. And so this is going to be associated with the enthalpy change when you go from a liquid to a vapor. A related latent heat that we'll also encounter is the heat of condensation. Okay? And really all the heat of condensation is it's just the reverse of the heat of vaporization. So rather than going from the liquid to the vapor, heat of condensation is talking about going from the vapor to the liquid. And so because of that, the enthalpy of condensation, or the heat of condensation, is just going to be equal to the negative delta HV. Right? In fact, I've used the word heat here, but probably a better word to be using is enthalpy. So as we don't confuse this with the actual Q value in our energy balance. Though the reason that you see these called heats of enthalpy or heat of vaporization, heat of condensation, is due to the fact that these terms were defined before we really knew the difference between heat and energy. Okay? All right, in any case, so enthalpy of vaporization and enthalpy of condensation deal with liquid and vapor phases. The enthalpy of melting, on the other hand, deals with phase changes going from the solid to the liquid. So enthalpy change of solid to liquid. Okay? And then related to that, the enthalpy of fusion is just the reverse as well, as we saw on the previous plot. Okay. And so not only can we go from solids to liquids, but we could also even go from solids directly to the vapor, right? And so this phase change is known as sublimation. So the enthalpy of sublimation so delta HS, enthalpy change of solid to vapor. Okay. All right. And so these different types of latent heats that we can encounter are typically tabulated, just like many of the other enthalpic and internal energy values that we deal with. Recorded in tables. And so in our textbook, table B1 actually records quite a few enthalpy of vaporization and enthalpy of melting values for various chemical species. So if we go to the textbook, you could see in the middle column, or the middle two columns here, we have one column for Tm, that's the melting point temperature of the species, and then to the right of it is delta Hm, which is the enthalpy of melting for that same species. All right. Next to it is Tb, which is the boiling point temperature for a species, and next to it is the delta Hv, which is the enthalpy of vaporization. And so we can see this recorded for quite a few of the chemicals in this table. Now, what I want to mention here is that the delta Hm and delta Hv, and even the melting point and the boiling point temperatures, those are all for systems or chemical species that are at a pressure of 1 atm. If we were at a different pressure, then those boiling point or the melting point temperatures would be different due to the fact that we're at a different part in the phase diagram.